Okay, dokie. Work and energy. Episode 790. Alright, so, oh, ouch, banged my knee. Now, what are we going to do here? What's work and energy? Well, there's some complexity to this, as I've mentioned in other videos. So let's just sort of talk about where things come from. And this is one of the problems with starting here, is that there's a lot of stuff that happens before this. One of the background pieces to this is when you learn about physics, ultimately what we're trying to do is describe, the world. And in mechanics, we're trying to get a sense of what's going to happen. If we know some information about some object, I want to be able to say what it's going to do later. If I throw a ball, where is it going to land? If I drop a ball, how fast will it be going? Right? I want to describe its, position, its velocity, its acceleration, its, the forces on the object. And this is what we're interested in because we want to be able to more or less predict, right, or describe or explain things that are going on. So when we start in a physics course, we often start with stuff that doesn't move, but when we get into things that are moving, we start looking at the forces acting on the object and what they do to the motion. And we usually start with a time perspective. We figure out the position of an object and we ask how quickly does it change position and in which direction. And we start looking at rates, right, which is, something per time, like, miles per hour. It's a rate at which you travel. If I'm going 30 miles per hour, that's the number of miles I go per hour, right? It's a rate at which I cover a distance. Now, we generally write these things as functions of time, so we're looking for the position of something maybe as a function of time as it moves through the world. And we develop, from this, we take our position in one direction and we take it to a velocity by taking the derivative. If you're into the calc-based physics, and you take the rate of change of velocity and you get acceleration. And these things are related to the net force. The net force on the object. And we develop functions of time, position and velocity is a function of time, and that's great and all. So I get an equation that says, if I have some force that gives me some acceleration and I have some expression with this, I can say how fast at t, or after, t seconds, after 6 seconds, what's it doing? That's cool and all, but what if we want to know how fast something's going, its velocity perhaps, or in this case, how fast it's going, its speed, after some displacement, right? So after, an object has been dropped, off of the edge of a perfectly good, roof, what's it going to do? It's going to fall, right? And maybe it falls, 15 meters. How fast is it going after that? That's not a dependence on time question. So we start saying, can we construct a model for this? And we do this, and maybe I'll make a video on work specifically and go into the details here, but basically what we do is we say, for an object, there's some set of forces on it. And the forces that go along the displacement, that means the forces that are pointed with or against the motion, the direction of motion of the object, will cause it to speed up or slow down. And we can sort of build an equation, and often you'll see something like the work done is how we define that thing. It's a name we give it, but we didn't start that. We started by saying, well, if it's a force and we use what's called a dot product, and we go along some displacement. Right, this basically selects out the force along a displacement, and this sort of says, okay, we only care about the things along it, so this sort of eliminates the things that aren't, gives us with and against, which is the speeding up and slowing down, and then we do is we just add them all up. And we might write something like work equals the integral of f dot dr. Okay, and if you're not a calc fan, and you're just watching it for fun, all this is a sum. Okay, so if I'm trying to get from here to here along this path, basically at any point if I'm pushing with some force, get red back on there, come on red, some force in some direction, and at that moment I'm moving in this direction, all I'm doing is selecting out the component of this force along this direction, how much of this effort is along this direction, and multiplying them together, and then when I get to somewhere else, I might be pushing in this direction, but my displacement now is this way, and I'm just basically getting all the little contributions along this path and adding them up. It's no magic there. And again, these are things we can get into. Remember I said once upon a video that there's a lot of layers of complexity, and you can start in the middle and work your way out as needed. So this is really just sort of saying what I'm doing is I'm adding up all the contributions of the effort to move the object along the direction that it's moving. And if we do this as net work, because we look at the net force, which relates to the acceleration of the object, we can write this essentially as ma, which is the net force dot dr. And in another video where we do work extensively, I can show you that the outcome of this integral from some place to another, or this, we always use definite integrals, but I'm just sort of playing here. We can show that the result of this will be something that looks like 1/2 mv final squared minus 1/2 mv initial squared. Again, couple steps in between, but that's not the point. The point here is that if I look at the effort to move an object along a displacement, I can get some quantity that looks like this. And basically, this is the mass of the object, and this is the speed squared. And there's a difference. What we say is we call this thing K, which is kinetic energy, which is of course just something we named it. Okay, this is just names. We can call it Frank if you want. Where K is given as 1/2 mv squared. So what we have here really is the change in K. Delta is change, and it means what happens is if I apply a net force through some displacement, that's a process. I take a box, and I push it around my room. I push it and get it sliding around the room. It was initially at some initial velocity, and then at the end is at some different velocity. It could be faster or slower. It could be the same velocity, depending on the outcome. If it's at the same velocity, this would be 0, and the net work would be 0. And basically, we can figure out that if we're doing net work on an object, that process of doing something to the object can change this quantity that the object has. So it can have kinetic energy, and the kinetic energy can change by an amount that's determined by the work done on the object. So the work changes energy. So what is energy? We still don't really have a good idea here, right? We're just naming things. So my favorite, used to be my favorite, it's one of my favorite things now, is what we call the work kinetic energy theorem. And it just states that if there's net work done on an object, the speed changes. That's it. Alright, the kinetic energy changes. Now, what does that even mean? Well, kinetic energy is what we consider energy of motion, and that may or may not be the best way of saying it, but that's what we call it. It's energy associated with motion. What does that even mean? Well, I don't know. It's an abstract term. What is it? Well, it has to do with the mass and the speed. And if you think about that, you can have objects like baseballs and bowling balls, And they could be going the same speed, right? They could both be going 10 miles per hour. But let me ask you this. Is it the same? Because they're both going 10 miles an hour? Absolutely not. One weighs like, hundreds of grams. The other one weighs, between 6 and 16 pounds, right? There's a significant difference. So energy is sort of a descriptor of the object and its motion. And it might tell you, for example, if it has some amount of kinetic energy, what does this tell you? Well, it tells me that I need that to do that much work to stop it, but I also needed to do that much work to get it going that speed. And if I change its speed, it's telling me how much effort, how much force do I have to apply, and through what displacement, right? And that matters in the sense of, think about throwing a baseball. If I stand here and I just take my arm and put a baseball in it and then hurl the ball this way, my arm ends up looking like this, and the ball went through basically this displacement. Now if I really want to throw the ball, I wind up, right? Get the ball back as far as I can, and then I throw by lunging forward, on this foot, stepping off my back foot, throwing my arm as far forward as I can, and now what you see is the ball has gone through a much larger displacement. So now I'm applying a force through larger displacement, which means I'm doing more work on the ball, which ultimately gives the ball more speed. So when you're throwing a ball and you're a pitcher, you want to get as much distance, displacement between start to finish, and that can come in the sense of rotations. You can twist and contort and throw and step and all these things, but ultimately to get a faster ball you have to have more work done on the ball before it leaves your hand. And that's basically, in a nutshell, what work and energy is. Work is like the effort, this process that you're doing to change the energy of something, in this case kinetic energy. And in that sense, that's the only energy there is. And this is where, in the textbook world, things more or less start. Always work and kinetic energy. And from there, they try to introduce some other forms of other things, and they do it in sort of a clever way. But they generally don't describe it really well in my dealings with textbooks. So the work net is the work done by all of the forces on an object. But we'll say not all forces are created equal. There are groups, and what we do is they break them into two categories. So the network will end up being the work by what they call conservative and non-conservative forces, or what they might call path independent and path dependent. And I'm here to tell you, physics people and probably other disciplines name things terribly, because I'm gonna do a video here soon, probably on work, and there are some things I can't stomach the way they're said and the way they're written. And it's because people that understand or think they understand just use things. We sometimes blindly use things without really thinking about it. And some of the examples they use boggle my mind. And I had a bunch of people arguing over some of these once upon a time, some faculty at a place when I was a grad student. Don't tell. And it was really interesting to watch, because how we buy into things depends on what we do. And what we find is that there are textbook people, and textbook people sometimes have glitches, and if you catch them on this, you can really bother them, and it's a lot of fun. So I like to bother the textbook, and it's important to understand what these forces really mean and what work and what energy really means in the context of how you use it, in the sense of in the real world, where you do this work equation, and then in this application as to where the energy comes from. And this is where the discrepancies can come up. But anyway, that's for another video. A ton of fun. I love work and energy. It's one of my favorite things. So the idea though is this equals the change in kinetic energy. And what they do is they say, well, these path-independent conservative forces, which in basic mechanics is just gravity, and sometimes ideal springs, but we'll come back to that. They're so special they get to go to the other side. So instead of writing work net, what we'll do is we'll write work by non-conservative forces equals the change in kinetic energy minus the work by conservative forces, and since minuses are so negative, we just give it a new name, plus delta U. And that is potential energy. It's not really potential energy, it's the change in potential energy. And the thing that bothers me here is the change in something makes it sound like it's something you can have. Can I have potential energy? Not really. It's a fictitious idea. It's a change. This is work, which means it's really related to a process, but it's a special process that we'll talk about another day. But what it really means is that it's really the difference that matters. If we change this, if this changes, we can end up with some expression. And what we generally do with bar charts, we might draw something like, if we look at the system, we say the system has some initial energy, has some final energy. Well, it can have some kinetic energy and some potential energy, and then it has some kinetic energy and some potential energy. And these can sort of exchange personalities. So if I had like 2 blocks here, 1 block here, and now I have 2 and 1, I basically have 3 blocks of energy here, 1, 2, 3, and I could have 1, 2, 3 here, and energy is what they would say conserved, which would imply there's no non-conservative forces, which goes in here in the first instance of this. But what if I had a system where I ended up with extra block here, block 4, that had to come from somewhere? It had to come from one work of non-conservative. So I had 3 plus 1 equals 4. So this work allows me to add energy in or out. And an example of this where you might end up with more energy could be on a skateboard. Now I can be careful here because I'm using potential energy. But a nice example of this is if you're not moving on a skateboard, you kick and you give yourself some energy. So you do work. That energy then is dissipated by friction in the wheels and drag, and that's negative work and takes the energy back out, and then you kick again and you basically are putting energy in, taking energy out, in a nutshell. So what we have then is this idea of potential energy and kinetic energy, and again I'm happy, and I probably will look at each of these in more depth, but this is just sort of a basic setup. So we have these types of energy, and we just keep track of them. So energy is really like accounting. We're just sort of keeping track of what types we have and where it goes. And potential energy, again, is sort of a bad name. A better name for potential energy, in my opinion, is energy of configuration. Because what we'll find when we talk about these types of energy is, we've already said that kinetic energy is associated with motion. Well, potential energy is almost, I was just going to say always going to want to use the word almost always or mostly, because sometimes there's exceptions, and I don't want to put my foot in my mouth. But this potential energy, capital U, is associated with the configuration. Something like, here's the Earth, and here's you. If you're way above the Earth, that's one configuration. If you fall towards the Earth, that's a different configuration. And the difference in potential energy, this change in potential energy, will be related to this change in height, which is a change in configuration. So configuration energy is actually a better name for potential energy because, in effect, that's what it is. It's associated with location. So this is sort of like where, and this is like, going, right? It's moving. So we have these two things, and these two things more or less define what we call mechanical energy. That's kinetic energy plus potential energy is the mechanical energy. And we can define these equations and use them. And what we find is that work by non-conservative forces can change the mechanical energy of a system. And the mechanical energy is very generic. It's literally related to position, right? The where, and the moving, right? Kinetic energy and potential energy. And everything else gets rolled into here, and what happens is we then start to investigate this and what other types of energies that aren't mechanical do we have, like thermal energy and nuclear energy and all these other energies, and then we start building from this. So this is essentially our basic building block of a system, and we can delve deeper into the energy as well in each of these, and I will. Like I said, there's so many things to talk about, but what I really wanted to do here is just establish this idea that this is very mechanical, again, no pun intended. It feels very equation driven, and it really is, because it comes from, in a nutshell, you have to learn about forces. So you learn about what forces are, and you build models, and those models lead to equations. From those equations, we can use those equations to derive other equations, and we get things like this. And then we have to decide what it means, right? What does it mean to have kinetic energy? And the way we look at it is we start exploring things like throwing balls and looking at bowling balls, and we get equations, and then someone says, let's look at work by all these forces, and we find that there's some special behavior of some of the forces that the others don't have or are different, and we then categorize them. So we take our simpler models and we build more complex models, and you say, well, why do we do this, right? That's the other thing is, you start learning this stuff and you have to ask yourself, why? Well, at the end of the day in physics, there's a textbook called Matter and Interactions, which is actually a great set of books if you really want to get a sense of physics. It's not equations and more equations. It's what physics is. Physics really looks at matter and, particle nature or whatever it is, stuff. It looks at stuff, how that stuff interacts with other stuff. And that generally, always is about force. And in physics, force is the interaction. And that interaction causes changes, or can cause change, or it can hold things, unchanged. But it causes change, and ultimately that's our goal, is to understand what happens when matter and things interact. And forces is one way to do that, but we get some situations that are just too complex, or more complex than they need to be mathematically. Yuck. So we look for other tools. And energy is one of those tools we develop to solve problems that are ordinarily more difficult to solve. For example, if I have an acceleration as a function of position, I can't use the same, if I have a force that's constant or varies with time, then I can solve in a very simple way quite often. But if I'm looking for something as like acceleration as a function of time, but I have forces that are functions of position, it becomes difficult, and I have to try other methods. And after you understand forces, really that's all this stuff becomes, is you looking at clever ways to use alternative methods to develop ways to solve complex problems that ultimately leads you back to what are the forces. And this leads to doing great things. One of my favorite examples, of course, going from energy to force, and in the case of gravity that would be mass, but in the case of charge, you can look at the polarization and depolarization of the heart. And we can work back from an energy perspective to forces, to the charge on the heart, and you can build a map of the charge on the heart by looking at the energy related quantities and get EKG, right? Electrocardiogram, right? So there's a lot of neat applications, but there's a lot of depth and it takes a lot of time. And I just kind of wanted, again, these videos aren't meant to do much other than sort of spark some conversation or some curiosity. Each one of these is sort of jumping into the middle, and what we need to do then is say what's important to learn and how do we learn it, and where do we go from there. So I think what I'm going to do is take a break and then ponder some video that I want to make next. Probably something on work and energy. So I'll just start doing is when I'm going to take this video as a starting place and then move out in different directions. So if you have specific questions, let me know and I can tackle them. Or if you just want to watch, great. Or if I'm talking to nobody, then that's fun too. So have a good time, enjoy the world around you, and ask lots of questions.